Hello, everyone. I am Yifei Zhang from the Beijing Institute of Technology. Today, I am delighted to share our team's recent work titled AI-Empowered Channel Semantic Acquisition for 6G Integrated Sensing and Communication Networks. This paper has recently been accepted by IEEE Network, and you can find the source code available on GitHub. For further information, please visit our group's homepage, which is linked below. Today's presentation consists of 5 sections: Introduction, Overview of the State-of-the-Art, Proposed Joint Communication and Sensing Channel Semantic Acquisition Scheme, Open Issues and Future Directions, and Conclusions. The future 6G mobile communication network is expected to support a wide range of intelligent applications and services, necessitating not only increased network capacity, transmission rate, and reduced latency, but also advanced sensing capability. Among numerous studies, ISAC stands out as one of the most promising and potential technologies to meet the aforementioned demands effectively. Meanwhile, AI presents opportunities for achieving synergy between C and S. The recently introduced channel semantic, in particular, offers a new perspective for ISAC signal processing. The concept of phased MIMO radar, adopting the HAD-MIMO architecture, emerges to achieve a trade-off between phased array and MIMO radars. This similarity in the hardware design allows C and S to be integrated into the same devices and systems. Besides, C and S also exhibit many similarities in signal processing, such as beam training and target searching, beamforming and target tracking. These shared characteristics create additional possibilities for accomplishing C and S using the same resources. However, communication aims at improving the efficiency and reliability of data transmission, demanding high spectral efficiency and the capability to combat channel fading. While sensing requires good ambiguity function, large signal bandwidth, and long coherent processing interval to achieve high-resolution target sensing. Hence, the signal design of ISAC requires a balance between the performance of C and S. Following this, the ISAC signal processing emerges as a consideration. Although processing methods dedicated to sensing or communication might remain applicable, they fall short of effectively exploiting the benefit of mutual information. The novel characteristics of new ISAC signals pose challenges for achieving effectiveness and precision in the design. Waveform design and signal processing play key roles in ISAC systems. Specifically, waveform design focuses on achieving C and S using shared resources. Depending on the type of the primary waveform, it can be categorized into sensing-centric, communication-centric, and joint design. Signal processing encompasses the encoding and decoding of communication symbols, as well as the detection and estimation of sensing targets. In this section, we present a comprehensive investigation of state-of-the-art waveform design and signal processing schemes, followed by a discussion of their limitations. While utilizing classical waveforms such as OFDM and chirp signals can accomplish C and S tasks, a well-designed waveform tailored for ISAC typically achieves superior performance. The SIDFTSO-FDM proposed in 8 provides lower peak-to-average power ratio than OFDM and integrates sensing through a frame structure with data and reference blocks. Besides, it is robust to delay spread with a flexible guard interval scheme. The proposed scheme in 9 can adapt to fast time-varying environments and serve high-mobility UEs. The adaptive virtual waveform design in 10 achieves a trade-off between C and S performance, using the Kramer-Rao bound metric for sensing and a novel distortion minimum mean square error metric for data communication. Expanding on the groundwork in 11, a low-complexity Riemannian conjugate gradient algorithm is proposed to flexibly balance C and S performance. Despite the efforts mentioned above, there still exist several critical issues in waveform design. The performance of waveform designed in Doppler and delay domains has received significant attention, while the angular domain, which is the most important domain in multi-antenna C and S channels, appears to have been overlooked. Although efforts in waveform design have taken into account the balance of ISAC performance, design of the frame structure is relatively inflexible and fails to achieve synergy. There remains potential for enhancing the extraction of C and S information, particularly concerning the utilization of prior information about specific channels to further optimize waveform designs. Signal processing for ISAC based on multi-carrier multi-user HAD-MIMO systems is challenging. In 12, the music-based AOA estimator is designed under the HAD-MIMO. The proposed hybrid beamforming scheme in 7 can simultaneously communicate with UEs and track targets. The proposed CS-based scheme in 9 effectively overcomes angular ambiguity brought by the WSA. The proposed SensingNet and ComNet in 8 can jointly estimate sensing parameters and demodulate data symbols during passive sensing. Nevertheless, considering the generality and synergy of C and S, the aforementioned schemes still have their limitations. While capable of achieving communication-assisted sensing or sensing-assisted communication, these approaches have not yet realized synergy through joint processing of the two modalities. These schemes primarily focus on feedback-free TDD systems and are not applicable to FDD systems. This limitation arises due to extra large-scale receivers required for FDD systems, leading to unaffordable hardware costs. Furthermore, in the FDD mode as well as the high-frequency TDD mode, perfect uplink/downlink channel reciprocity does not hold, which requires downlink CSI feedback from UEs. However, relevance between communication feedback and sensing has not been considered in these schemes. Next, we will introduce our joint communication and sensing channel semantic acquisition scheme. Consider an ISAC system shown in Figure 1. The BS adopts a uniform linear array with M antennas, where the fully connected HAD-MIMO with KRF chains is employed. Additionally, a single sensing antenna is deployed for downlink active sensing, offering the advantages of minimizing the hardware costs and energy consumption. Furthermore, we consider that the BS simultaneously serves K single antenna UEs and employs the CPO FDM with NC orthogonal subcarriers to combat the frequency selective fading in broadband transmission. Regarding the channel semantic extraction, we introduce a two-stage frame structure for TDD systems with imperfect RF calibration and FDD systems, as illustrated in Figure 2. The guard period is indispensable in TDD systems to avoid collisions between echoes and UE's feedback, while it can be removed in FDD systems. In the first stage, the basic pilot is transmitted for rough extraction of the sensing channel semantic, which is then utilized to design the enhanced pilot. Considering that the dominant paths in C/and S channels are partially similar, the enhanced pilot can improve the efficiency of respective channel semantic extraction. To achieve synergy, we propose a DL-based joint communication and sensing channel semantic extraction and reconstruction network, called JCAS CasterNet. The block diagram of the proposed scheme is shown in Figure 3. JCAS CasterNet can be partitioned into 3 components: ComCasterNet, SensCasterNet, and the shared module. Global optimization is achieved through end-to-end training. Moreover, the allocation of pilot symbols in the 2 stages, combined with the weighting of loss functions, can accommodate the degree of sharing between communication channel semantic and sensing channel semantic, and the trade-off between the C and S performance. During the first stage with the basic pilot, UEs can acquire downlink communication CSI, and the BS can be regarded as a monostatic radar. The uniqueness lies in the fact that the radar receiver consists of only a single antenna. Leveraging the fact that the AOD and AOA in monostatic radar are the same, reconstruction of the sensing channel can be formulated as a CS problem. Contrasted with the enhanced pilot, the trainable basic pilot, although lacking the adaptability to specific samples, demonstrates generalization ability in diverse scenarios. The increasing overhead of the basic pilot assists the design of the enhanced pilot, promoting the utilization of sensing channel semantic. While in the case that a substantial difference exists between C and S channels, this would potentially result in limited improvement in communication benefited from sensing. Additionally, the reduction of the enhanced pilot symbols reduces the adaptability of the scheme, which might lead to an overall performance degradation. Yet, conversely, insufficient basic echoes hinder the effective design of the enhanced pilot. Therefore, a proper allocation of pilot symbols at 2 stages is crucial. Indeed, the sensing antenna at the BS can be viewed as a virtual UE, which can share the received measurements with the BS for the second stage processing. In this manner, during the second stage of channel sounding, the virtual UE and real UEs form a distributed multistatic radar system. Here, the real UEs can be regarded as a type of passive sensing receivers. Based on the measurements of basic and enhanced pilots at 2 stages, real UEs respectively can extract the communication exclusive channel semantic and the C and S common channel semantic, and then feed them back to the BS for ISAC design. In this distributed sensing system, feedback and echoes can be collaboratively processed, resulting in the synergy of C and S. For the reconstruction of communication channel semantic, we adopt ASE per UE as the loss function. The goal-oriented approach enables UEs to eliminate redundancy and embed the essential semantic required for beamforming into the feedback. As for the reconstruction of sensing channel semantic, directly fitting the AOA would bring several issues. In contrast, the channel subspace is relatively simple to reconstruct and contains all the necessary information needed for AOA estimation without redundancy, as proven by algorithms like Music and Esprit. Given the rotational invariance of the channel subspace, we employ cosine similarity as the loss function. To demonstrate the superiority of the proposed scheme, we study a representative case in the massive MIMO-based ISAC systems. The simulation parameter settings are summarized in Table 1. GMMVSOMP is employed as a benchmark for CS algorithms, as optimization-based iterative algorithms converge slowly in this case. Following the reconstruction of the sensing channel, angle estimation is accomplished using the music algorithm. Besides, the DL-based CSINet is adopted as the baseline solution for downlink communication CSI feedback and reconstruction. With the reconstructed communication channels, the benchmark schemes employ EGT and RZF to design the downlink hybrid beamforming. Ablation experiments are conducted using ComCasterNet and SensCasterNet separately without mutual information to demonstrate the synergy of C and S in JCAS Casternet. To validate the effectiveness of the frame structure and the enhanced pilot, the random pilot is utilized as a benchmark for comparison. Figure 4 shows the ASE performance achieved by different schemes versus the data SNR at different pilot SNRs. For the JCAS Casternet, the echo SNR is set to 10 dB. It can be observed that the designed pilot performs better than the random pilot, demonstrating the effectiveness of the proposed frame structure and the enhanced pilot for communication. Moreover, the proposed methods outperform perfect CE, CSINet, EGT-RZF, confirming the superiority of channel semantic acquisition techniques. On the other hand, schemes with GMMVSOMP CE, perfect CSI feedback, EGT-RZF is inferior to perfect CE, CSINet, EGT-RZF, validating that the bottleneck of the baseline methods largely stems from the limited number of pilot symbols. While ComCasterNet manages to partially mitigate this issue via channel semantic acquisition, JCAS Casternet consistently shows superior performance with around 1 bps per hertz. This result underscores the benefit of integrating sensing capabilities to enhance communication performance. Figure 5a and Figure 5b respectively depict the cosine similarity and NMSE as a function of echo SNR. For the JCAS Casternet, the pilot SNR is set to 10 dB. Constrained by the limited number of pilot symbols, the benchmarks suffer a significant performance loss regardless of the echo SNR. However, the approaches with the enhanced pilot still outperforms those utilizing the random pilot, reconfirming the effectiveness of the proposed two-stage frame structure for sensing. Furthermore, the SensCasterNet-based pilot design achieves better performance than the JCAS Casternet-based pilot design. This confirms the earlier analysis that power allocation in the angular domain becomes inevitable for the enhanced pilot to ensure the communication performance because of the partial dissimilarity between communication AMD sensing channels. The enhanced pilot designed in JCAS Casternet cannot dedicate to sensing like SensCasterNet, which consequently leads to the degraded performance in sensing channel semantic reconstruction. Nevertheless, with the assistance of UE's feedback, the gap between the sensing performance of JCAS Casternet and SensCasterNet remains minimal. Figure 6 provides additional insight into the performance of channel subspace reconstruction with different loss functions at an echo SNR of 0 dB. By transmitting different pilots on different subcarriers, the proposed approaches capitalize on the identical channel subspace across different subcarriers so that the angular information can be reconstructed with fewer pilot symbols than the target number. In the scheme with NMSE as the loss function, the orthogonality between the channel subspace and noise subspace is disrupted, resulting in the angular spectrum at certain positions being nearly overwhelmed by noise. In contrast, cosine similarity enables a more precise reconstruction of the sensing channel semantic. DL-based channel semantic acquisition offers opportunities for ISAC networks to realize synergy, yet the progress still confronts a range of challenges. In this section, we succinctly outline some open issues and promising directions for ISAC networks. Firstly, channel modeling of ISAC networks. As mentioned above, leveraging the correlation between C and S channels can reduce the pilot and feedback signaling overhead, enable seamless synergy between C and S, and ultimately improve the overall performance of ISAC networks. However, it remains unclear how to accurately model this correlation in practical environment. In the current stage, the common angular information of objects serving as both communication scatterers and sensing targets has been widely adopted, yet discussions about other crucial factors such as cluster structure and energy distribution are relatively scarce. Hence, the lack of precise channel models of ISAC networks has limited the exploration of synergy schemes. Secondly, synergy performance analysis under explainable AI. To gain a deeper comprehension of ISAC systems, synergy performance analysis is essential. Furthermore, the current training approach of weighting the C and S loss functions is still rather rudimentary. Reliable synergy performance analysis can also provide more accurate objectives for DL-based ISAC schemes, guide the design of network architectures, and improve the explainability of AI. Although the information theory of ISAC has yielded some preliminary results, many practical constraints have not been taken into consideration. With the analysis of synergy performance, it is believed that we can attain deeper insight into the criteria of AI-empowered ISAC networks and accomplish a higher level of synergy. Thirdly, lightweight deployment and multi-BS sensing. AI technology, while boosting the performance of ISAC networks, imposes increased demands on computational resources. To reduce hardware costs and inference overhead, further research on lightweight deployment for ISAC networks, such as quantization, pruning, knowledge distillation, etc., is imperative. Additionally, this paper only considers ISAC design with a single BS, but multi-BS sensing is also important in practical scenarios. For instance, when multiple targets are detected within the sensing coverage of several BS simultaneously, target association becomes necessary to determine which parameters sensed by different BS correspond to the same target. In order to implement ISAC technology, lightweight deployment and multi-BS sensing are indispensable. Last but not least, security issues of ISAC networks. With the emergence of 6G and its intelligent applications such as remote health, V2X, and smart home, a substantial amount of personal data is being delivered, giving rise to concerns about the security of ISAC networks. Sensing requires the transmitted waveforms to thoroughly interact with the wireless environment, rather than just serve the UEs in communication. The interaction not only embeds target parameter information into echoes but also poses risks for eavesdropping and privacy leakage. Currently, research on the security of ISAC networks is still in its early stages. Striking a balance between security and efficiency stands as a pivotal topic for future explorations. Finally, we conclude our work. In this paper, we introduce an AI-based channel semantic acquisition framework for ISAC networks, achieving synergy between C and S. To begin with, we conduct a comprehensive overview of the state-of-the-art solutions encompassing waveform design and signal processing, while also discussing their inherent limitations. Considering the correlation between C and S channels, we propose a two-stage frame structure along with the channel semantic learning-based JCAS CasterNet, which yield gains in both extraction and reconstruction of channel semantic. The case study demonstrates that the proposed scheme achieves improved overall performance even with extremely low pilot and feedback signaling overhead. Finally, we highlight the challenges that ISAC networks encounter in its development and outline potential research directions in the upcoming 6G era. Here are some main references for the slides. To find more information about this work, please refer to the original article below the video. Thanks for your attention.